All right, all right. So I guess I'm the last one that gets to say good morning. We talk a little bit about sets today. It's good to be back in Texas. It's been a few years. So I'm Andy Fundinger, and this is Always Use Sets. So I always find it's more useful than giving a year to talk about which Python version I started with. So when I started learning Python, the book said, learn Python 2.2. Then they had a little slide that said, newly revised for Python 2.3. And Python 2.4 had just come out. So that's where I start from. I've worked with Plone, I've worked with Twisted, I've worked in the financial industry, I've done a little bit with virtual world stuff. I've been at Bloomberg since about 2017. In 2019, I went over to our system reliability engineering groups, and in 2020 to data services, or DNA, which is why they put that on my fleece. I work on something called our data gateway. It sits in the middle of a lot of our workflows. We're a gateway, so all the code around me is owned by other people. Both upstream and downstream is other people's code. We have billions of requests per day going through there and millions of semi-independent code paths. This is easy to imagine when you realize that our queries are something like, what is the price of this security? Well, if the security is a stock, that's easy. You go to the exchange, see what the last price was, you send it back. If it's a bond, there's this whole pricing thing that you need a bunch of information and then you can do. If it's an index, you need the price of a whole bunch of other things and then to figure it out, and then you can send that back. And that's where our code paths just multiply. So a lot of what I do day to day is ingest telemetry data and process it a bit to understand what's going on in a complex system. Of course, today we're talking about sets, and that means we need to talk about all the data structures. So we'll start with tuples. Tuples we declare with parentheses. They're ordered, they're frozen, they're immutable, and you can have duplicate items. Lists, we go to the square brackets. They're ordered, they're mutable, you can have duplicate items. You may imagine this won't be our only slide about what sets do. But they use the curly braces. They have to be a collection of hashable objects. They are unordered. If you want them to be immutable, you can use the frozen set. And all the items have to be unique. The dictionary, we add the colons to the curly braces, and we have a map of hashable objects to other objects. As of Python 3.6, they are ordered. Sets are still not ordered. We'll come back to that. And all the keys have to be unique. The constraint here is not just that they're unique, it is that they are hashable, which means dunder hash and dunder equal. And then there's one other that I want to put into this talk because it completes some rough edges. The counter, off in collections.counter, is a map of hashable objects to the counts of their occurrences, and all the keys there have to be unique. Now, the cool thing is this changes a collection of things with duplicates, where order doesn't matter, into a dictionary. So if you have something that would be a set, except it has duplicates, just refer to the dictionary section of the talk. Okay, so how do we use sets? We can declare them easily enough. There's a constructor. We have set comprehensions. We have an add method to add things. We have a remove method to remove things. Until we put in type hinting and start checking and start paying attention to the type checker, we can mix and match types in our set. They are also collections from the abstract base class collections, which gives them a few properties. Particularly, they are iterable. Thank you, Moshi. They have a length, and they have the in operator. So I can say, is this in my set? Yes. Is this not in my set? Also yes, because I chose the thing I removed. There are also some particular set operations, and this is where the real power comes from, because these operations are implemented down in the C level. We can union, which is take two sets and give us a set that combines everything in both of them. We can intersect, give us the set of things that are in both of them. We can difference, take this set, remove anything in that set. And we can symmetric difference, which is give us all the things that are only in one set, but not in both. Sort of the XOR of set operations. So, in mid-conclusion, always use sets. By using a set, we clearly communicate our expectations. We tell the people that it might be changed, but if more things are added and they duplicate, that's fine. If things are removed, they're removed, that we're going to check whether things are in there, that we don't care about the order. We communicate a whole lot by just saying this is a set. And this will perhaps not matter when you write an include list that's written one time in a constant and goes down into your code somewhere. But as you maintain the code, as you use it later, the fact that you made it a set from the beginning prevents the behavior from drifting and prevents anyone from having to ask, well, if we put it in there twice, what does that mean for an exclude list? And then the other one, because of those set operations, we can write algorithms based on discrete math. We can go in to our data structures and algorithms book, and it'll say, oh, just union the two things, and we can just do that. So it's like tapping into an extra stack of documentation. But I see there's some time left. So you might have some questions about speed. I thought I'd answer those. How do we measure the speed of something in Python? For something as basic as this, there's a standard library, TimeIt. It will work for this. If you're doing more benchmarking, then you want to use some of the tools that Carol talked about. So we'll check our help on TimeIt. It tells us that we give it a statement, a setup, a number, and then it tells us this is a convenience function for the timer object TimeIt method. So we should check our documentation on TimeIt, timer, TimeIt, which explains that it does all the performance timing stuff and returns in seconds how long it took to run all the iterations you asked for, which we might then want to divide by. So this is what TimeIt looks like. We see that declaring this 10-item set gives us 10 to the negative 6 seconds. 10 to the negative 9th is nanoseconds, so that's 1,000 nanoseconds or a millisecond. And I'll use that timing through the rest. The other question is memory. Again, we have a memory function, get size of. It's off in sys. This is probably the only time you would want to actually use that practically. The problem with the get size of function, whatever you give it, it gives you the size of. Now that sounds like exactly what you would want. It doesn't give you the size of anything in it. So when we're looking at the size of the set, it's telling us how big the set is, not how big the items in the set. If we took a dictionary, if you took a class that has stuff in it, that has stuff in it, that has stuff in it, it doesn't tell you any of that. But we're talking about sets, so this tells us what we need to know. And if you need more, may I suggest memory, which we open sourced. So what's the size of a set? An empty set is 216 bytes in Python. Okay, but it might matter a little bit how many items we put in the set. So let's go ahead and take a look at that. I am using the log of memory, so this is a log scale. Otherwise, things get very distorted. So we'll zoom in on 1,000 items, and I'll take that log scale off just so we can see it. Our set takes 32K. The tuple, or the list of the same size, takes 8K. So we do need to know set or frozen set just the same, dictionary a little bit more, that we are using a lot of memory when we're using sets. Oops. Okay. So how long does it take to construct a set? Well, obviously that depends on the size. Obviously I can put a big long log time graph of sets, frozen sets, sets, and tuples. And we'll just go ahead and acknowledge there is more than one way to construct a set. This is using the constructor with a list, generating, building, but the fastest is just to go to the constructor. If we look at 1,000 item set, what we see is it takes about 7 milliseconds to make a 1,000 item set with the constructor. By comparison, the tuple can do it in a millisecond. So we do have a bit of construction time. List also takes a millisecond, and I'm not sure if I'm hitting an optimization on that one. Oh, did I jump a slide? I think I jumped a slide there. Constructing a set. What about changing the set? So obviously this is going to get more interesting when we start changing it because it is a mutable type. And if we take a look at this, for some basic mutations, the set is a little bit faster than the tuple, than the list, sorry. And we'll just go ahead and add tuples in here and vary it both on the size and the number of mutations. But if we look at 1,000 items and we say, let's look at how many mutations we do, this is set. So if we're doing really any number of mutations, we see that doing the same mutations on a list or a tuple is taking much longer. We'll go ahead and pull that back out and ask the question, so how many mutations should we do to get a payoff? This is doing 10 mutations with different sizes of sets. So if we're doing 10 mutations and we have a set size of 10, it comes out about equal. But as soon as we're doing 100, we're really pulling ahead on sets here. Again, this is on a log scale. So that's basically the answer that I've found there. If you're doing 10 mutations, you should just go ahead and use a set for performance reasons in addition to clarity. Now, the next question is, what if order matters? What if we do actually need it ordered? So I'm adding an additional performance measure here. This is the mutate sort. This is do the mutations and then sort it to get back the order. And it turns out that while we do lose a little bit of performance to doing that sort, it is still faster than doing it in a list. So even if you have to sort it afterwards, if you're doing 10 changes, you might as well just use the set. But then we do have dicts, and dicts are pretty good. Dicts are amazing in Python because they underlie the entire class object structure, so a lot of work has gone into making dicts faster. In fact, sets were added in Python 2.3, so when I started learning Python, there were an awful lot of instructions on how to use dicts when you probably should have used a set, but they just came out. So I went into the code and I was curious. There is separate code for sets at this point. And there's this helpful comment that tells us what to expect. It says, use cases for sets differ considerably from dictionaries, where looked up keys are more likely to be present because you're probably going through an object asking for something that ought to be there. In contrast, sets are primarily about membership testing, where the presence of an element is not known in advance. Accordingly, the set implementation needs to optimize for both the found and not found case, which suggests that we should find the dictionaries are faster when the thing is there, and the sets are faster when the thing is not there. Testing has shown this not to be true. So they wind up being pretty even at a first glance, and looking at 10 and 100 this time, it turns out that a set search for missing is a little bit faster than a dictionary search for missing, and a set search when it's present is similarly a little bit faster than a dict search when it's present. So either way, if you're just doing the membership testing, you do get a benefit of sets. So that brings us to the set operations that we were looking at earlier. How do those fare, set versus dictionary? So I'm looking here at set for update and dictionary for update. So we find the set updates noticeably faster than the dictionary update. Set unions just the same. Set intersect is faster than using a dictionary to implement intersect. Difference, it's all faster, but is it faster enough? Like we saw with lists where we might as well sort it. We can, of course, implement these things so that we use a dictionary and then put it back together after using the set operations on the sets. So set difference looks like that. Set intersect looks like that. Pretty simple. For symmetric diff, there's two ways to do it, depending on whether you care about the values. I think if you don't care about the values, it might be cheating, but we'll cheat. So you can use the from keys to construct a dictionary where all the values are the same, and that may be interesting in one or two cases. The symmetric diff vals, we do have to go and maintain the values. So what I did was I went ahead and merged the dictionaries, did a set intersection, and then just subtracted the ones that were in both. Let's see how that does. Set operations 2. So we'll go ahead and add those. And it turns out, by taking a dictionary over to a set just to do intersection, you lose all your advantage. Same thing with difference. But symmetric difference, you do get a pretty good advantage if you can ignore the values. Again, that's cheating, but cheating's fun. But a small advantage still, even if you pull the values back out and put them together. So, the conclusion of this talk was written before the talk. The conclusion is always use sets. I hope that's not too much of a surprise. And the big reason is to add the clarity. By making it a set, you tell everyone maintaining it, including yourself in 6 months, more about what's going to happen and what's expected. They are faster than lists or tuples when even 10 items are changed. So even if you have to sort or do some combination later. Unfortunately, I also have to say do not use sets. And don't use them if you're running out of memory. Okay, about 4 times as big. If a dict is equally idiomatic, you're going to have to do some pretty heavy lifting before sets are going to pay off. I think of it as the line is symmetric diff. If you can take the keys off, do some set operations that are at least as complex as symmetric diff, and put it back in, you will get a performance benefit, and you and your code reviewers will have to think about the clarity benefit. But if you're not at least manipulating the keys in a few operations, they're not going to pay off. And you can just leave it as a dictionary. And with that, I will take questions.
Ooh. And I do have some questions for you. All right, are you ready?
No. Oh, yes.
Okay. We get ready in the question answering position. How much memory do you save over a dictionary with sets? Any good tools to profile their real world difference?
So there's lots of tools for memory profiling. Memory will work fairly well, and I think I have to say that. In terms of straight saving on the set, it was, do I have that? Wait. Straight saving on the set, it's like 30K on an empty one, and just kind of trivial. Let me bring this back up. Dictionary, 10,000 items. The set is 32,984. The dictionary, you're saving about 4K at 1,000 items.
Right. Okay. What did you do to measure mutation on a tuple since it's immutable?
Oh, I took them apart and put them back together.
Yeah.
Yes, don't do that. But for completeness, I did include it in the graphs.
How do you personally handle the non-determinism of set ordering across runs?
Probably either avoid having it be important. This usually comes up in your test cases by either using PyTest's ability to just handle the compare for you, or running a sort so that you can do a compare on it.
Right. And then can you explain what this is? And it was where you used times 10 to the 9th power?
Oh, yeah. So I got this tiny little number here, times 10 to the negative 6th. And I said, what is that? I'm going to be talking in 10 to the negative 6 seconds for an entire presentation. So I said, what is that? Oh, okay, 10 to the negative 9th is nanoseconds, so it's 1,000 nanoseconds.
There you go. Very cool. That was, looks like I got one more question that came in while we've been talking. Did you notice any difference between the performance of sets and frozen sets?
No. I did include them. They have a noise level difference in the cases where I included them, which are obviously before I start mutating. Here it is, and zoom it in. Oh, next one's the zoom in. So constructing the frozen set is 7,000 nanoseconds, and constructing the set is 6.7 thousand. So there is a slight difference there, but
frozen sets are still good for building a snowman, but I had to let it go. Last one. This will be the last one. Can you expand into that use case of exclude list you mentioned at the beginning, and any other real-world case that you've used them and liked it?
Yeah. So if you're doing some testing and you have a set, I'm going to test everything, and in our case, it was a number of machines. I'm going to test all the machines, except I know this one is a special case. So if anybody ever wants to run a test on that, just don't. Or just return an error that says this machine is not used for testing. So what we did was we defined an exclude list at a pretty high level, and then down in the code where it actually figured out which machines it was asked for, it goes, I'm about to run this machine. Is it in the exclude list? Yes. Then I will skip it.
Very cool. Well, thank you very much.